you make chemicals, you use so-called catalysts. You've heard something about the catalyst since your chemistry courses. Have you used something in a lab or so? But the way that catalysts work in the chemical industry is they're solids, and they're manufactured in such a way so as to maximize the surface area so that the liquid or fluid or gas with the reactant that touches the catalyst has the maximum surface area that it can contact so that you get more product. And what better way to make a catalyst than to build it as a porous particle like this, right? But smaller. Because you can imagine how much surface area there is in this thing. Okay? As much as normally as well, or more. Without exaggerating.
Yeah.
Okay. So we have this so-called catalyst particles. And many times they're just called catalysts. You know how they look? Like this. But much more porous than this. And then they are packed inside a so-called chemical reactor or packed reactor, catalyst packed reactor, upon which you're flowing a fluid that contains the reactant. The reactant goes through this stuff, not only on the surface that you're seeing, but on the several square kilometers that is inside this thing, and you get the product. You've heard that in some way before. If you haven't, do you understand it? Yeah. Now these catalysts come in the shape of those cylinders. They look like cylinders, pills, like cylindrical pills. Oh, thank you so much. This is fair. Thank you. And do you have your homework to give her? Or?
Yesterday.
Okay, afterwards. Put it in my notes. Sometimes these catalyst particles look like very flat, very thin wafers. And we're going to schematically depict them like this. So like a little coin, like a little dime, but very porous. They have pores on the surface. So that dime that you're holding has a lot of pores on the surface, holes, and these things go inside in a tortuous about way. And when you have that happening, the reactant is going to diffuse into the porous catalyst particle. It will react, it will make a product, which will come, of course, out. And you as engineer or the company will reap the benefits of the process. Usually, unlike very complex reaction schemes that you, of course, are masters of, organic chemistry especially, we're going to consider the simplest reaction taking place here. And the simplest reaction taking place is like A going to B. We don't care what that is. And there is the so-called reaction rate constant. So this K1 is going to be called reaction rate constant. It will have units that will depend on the rate of reaction that you have. Because you want the overall rate of reaction to have units of moles per second per cubic centimeter. Now remember that in the problem that we did last time, or 2 times ago, 2 lectures ago, with electrical wire, it was calories per, that's the generation term we call it. Whether it's heat generation or moles generation, that's the term of generation. In this case, when we have a reaction going this way, it so happens that instead of counting how much reactant is consumed, it is much more expedient. Matt, are you following? What did I just say?
So by how much reaction is consumed, it's much more expedient.
Wow, you just had me there. I thought you were not following. Very good. Okay? It's much more expedient to count how many moles of product are being consumed rather than how many moles of reactant. It's much easier to do that. So, the generation term, which is rate of moles per unit volume, of a disappearing or reactant. The reactant disappearing. And we're going to consider the easiest reaction rate expression is the so-called linear or first order reaction rate. In other words, if C is the concentration, the molar concentration of A, we say that the moles per second per cubic centimeter equals to K1 times C to the first power. And we call this a first order reaction. If it was to the 1/2, then it would be a square root order reaction. If it was the second part, it would be second order reaction, and so on and so forth. And through experiments, kinetic experiments that you do, you find those reaction rates. So K1 is a reaction rate constant. Specifically, the one on a subscript signifies first order reaction rate constant, because this is a first order reaction. First order means that the concentration of the reactant has an exponent of 1. First order, first part. Do we agree? Like this. You can still change. What grade are you? Meaning what year?
I'm a sophomore.
So,
Yeah.
it's possible.
A lot of things are possible.
All right. Is this more clear? So what is that? Now, so the engineering question now is The engineering question is a dumb question, right? How many moles per second of A are we consuming inside that catalyst particle? Right? What is the number of moles of A disappearing per second? Because if we know how many moles of A are disappearing per second in this pill, if we have 1,000 of them, we multiply by 1,000 and we have the answer for the entire reactor. We're going to specify that on the surface of this coin, there is a constant concentration, C0. In other words, we're furnishing the reactant. So C0 is the surface molar concentration of reactant. And then, of course, in order to answer that question, we want to have dC dx if we take the midplane of this and x starts from the midplane, so x is equal to 0 at the midplane, and x is equal to something else on the surface. What? What have we used for the slit flow that you also had in your exams, because you remember everything is related here, right? Remember the slit that you were asked to get the flow in the exam? Okay. Same thing. So it's going to be, we're going to see this as a slab. So this is modeled as a slab, this disc. And it is modeled as a slab because it is like a coin, which means that the rate at which reactant is coming from the top and the bottom of the coin surpasses, is far above and beyond the rate of reactant that comes from the sides of the coin, from the rim of the coin. We're ignoring that. In fact, if I'm going to draw this coin a little bit bigger in order to again have the midplane like so, x is going to be equal to 0 here, and x is equal to go to equal to b on the surface. Which means that if we were to have a so-called concentration profile, C as a function of x. Remember, this is the concentration profile of the reactant, and this is capital V, and this is C0, the concentration of the reactant on the surface of the coin-like catalyst is going to be the highest. It's going to be C0. In other words, this point here will be C0. And then we can easily expect that the minimum is going to be at the center or the midplane. If I were to draw the concentration profile here, this would be C0 and C0 on the bottom, and at the midplane we would have zero derivative for the concentration. Remember that this time you cannot find it many places, right? So you have to ask questions if something does not look. Are you following? 100%? Okay. All right. Anybody else I should ask? Mike? Who's Mike? There is no Mike here, right? Is there one? No. We have a class without a Mike. All right. So this is understood. Now, so we have here, this is the derivative, right, of the reactant, right, at the surface. dc dx at x is equal to capital B multiplied by negative, and I have not discussed this today, there's going to be net diffusivity or diffusion coefficient, molar diffusion coefficient, for the reactant that goes inside the catalyst. And what is that, what I have just written now? What have I written here? Well, Fick's law, which is, so it's the flux of reactant entering the phase. The flux means it has units of what, Caitlin? What are the units like? What are the moles per? You remember molar flux? The units of molar flux? Tell me. That's flow rate of moles. That's molar flow rate. Like people entering this room per second would be people flow rate flowing in. Okay. Moles per second is flow rate, it's not flux. It's a huge per meter squared. Very good. Perpendicular to the flow, right? So that's flux. Moles per second per centimeter squared. if I have this and I multiply it by 2a, where a is this area here, the area of the coin, the flat area of the coin, I have the answer. Because we have on the top, and then we have, of course, on the bottom, another a that multiplies that. Okay? Does this make sense? That if we have this, we multiply by 2a and we get the answer to the engineering question that said, how many moles overall per second are entering this? I don't have a coin again. Yes.
Does it not enter through the sides?
We're assuming it doesn't.
Okay.
We're making the assumption, otherwise it becomes a multi-dimensional problem and we cannot solve it at this stage. So we're assuming that the reactant is only entering from the top and the bottom. It's like if the side is insulated, the rim. Okay, is this clear? Okay. So we want, of course, a differential equation. To get that differential equation, we're going to consider a slice of thickness delta x. So if I redraw that infinitesimal slice, it's going to have thickness delta x, and it's going to be j times a at x minus j. What is the symbol for j, Harun? Molar. Molar flux. Okay? A at x plus delta x plus the rate of generation, which actually, in this case, because we're counting molecules or moles of reactant, it's going to have a negative sign, minus K1C, because we know that this is a first order reaction. I specify that on the left side of the board, times what lambda? Dylan. Cole.
Area?
Times?
Area?
Look at it.
Uh,
The generation term is always given moles per second per cubic centimeter, not per area.
oh.
In other words, we want to know in this thin slice of coin, that, in other words, it's a coin that is like infinitesimally thin, the slice, how many moles of reactant are disappearing per second? If we know the rate of reaction, which is K1 times C, it's in terms of moles per second per cubic centimeter, what do we have to multiply by Alex Bird?
Will it be volume?
Which volume? Of the of
the
that
slab.
thin wafer, right? So, equation.
Pi r squared.
No.
A times dx?
The area is A, and delta X is the volume. And this is the mole balance, steady state mole balance. Are you okay with that? Remember, if you don't understand, you must stop me, right? Yes.
Does the porosity make any difference? Because
The
that's
balance is all over the same.
okay. Because that's the volume of the entire wafer, but there's only a certain amount of holes inside the wafer, right?
Yes, that's taken into account because this generation, or in this case it's negative generation term, is in terms of not of volume, of void volume, but of overall volume.
Okay.
So you don't have to deal with epsilon or anything like that. Yes.
So what's the unit of J?
What?
The unit of J.
It's flux, moles. That was the first time I discussed these things, 2 times ago or 3 times ago. was the law of fixed law, right? Where J was equal to negative delta dc dx. And I did tell you, right, that if you have not reviewed the previous stuff, that's fine. To ask me questions, absolutely, stop me. But next class, we have one more class, and that will be the hardest class. If you don't study between now and Thursday, it will be less comprehensive. But still, if you have problems or questions, please ask, yes.
So general question, so you have the reactant flowing in from the top, bottom and the top.
And the top, yes.
So
As stuff is coming from the top, it has the highest concentration here. As it goes in, the concentration is becoming smaller, smaller, smaller. It's becoming minimum. And then it grows towards the other side. Because the other side is mirror image of the upper side, of the upper half. The midplane separates the coin into upper half and lower half. The upper half and the lower half are mirror images of one another.
so at steady state, is there still flow coming in? Because I mean,
You don't. This is not a flow problem. This is my molar diffusion problem. You don't consider at all flow. Because you specify that at the surface you have this concentration. And that's how it's done. Now, the flow in a more advanced course, perhaps next year when you take reaction kinetics and reaction design or a graduate course, then you are going to consider the whole problem and flowing of, through in between the particles. But we don't consider that. Here we just look at one individual catalyst or catalyst particle. Other questions? Okay, so if this is our equation, A is constant and drops out. This crosses out, and then we get a differential equation, or the beginning of a differential equation that says J at x plus delta x minus J at x divided by delta x plus K1A, no, just K1C rather, is going to be equal to 0. Just change the order of the terms, multiplied by -1. And divided by delta x, which gives us this, after we take the limit as the derivative, dj dx plus k1c equals 0. What do we do next, Will? We substitute for j by means of fixed law. Very good. Fixed law. Fixed law says that j is equal to negative delta dc dx. So when we do that, we're going to have d squared c dx squared minus k1 over delta times c is going to be equal to 0. And that will be our differential equation. Okay? What are the boundary conditions for this? At x equals something, at x equals something else. Katie? At the x equals? Yes. Loud. Look at it. It is x is equal to 0 right here. What is the concentration? Remember, mirror image, right? If we drew the other side, it would go like that. Very good. dc dx equals 0. In other words, the derivative of the concentration is 0. There is a minimum. Okay? And Ning Hao. At X, second one, Ning Hao.
F equals
B, yes. The concentration is equal to what?
equals
C0, right? Ning Hao, have you seen an equation like this before? Differential equation, when? Very good. Very good. In fact, if we say psi being equal to x over capital B, this is going to become over B squared, which means we multiply this by B squared. And we haven't changed anything. If we also define as phi or phi a dimensionless concentration C over C0, our differential equation is going to be identical to what we had last time. D squared phi, d psi squared minus beta squared phi is equal to 0. At psi equals 0, phi psi, meaning the first derivative of psi is 0, and at psi equals 1, phi is equal to 1. Where of course beta is different, or beta squared is different than what we had last time. It is equal to, yes, you have it.
Yeah, what happens to the K1 over script? Like going from that to,
K1.
yeah, going from that to that.
Yeah, this whole group here
Okay.
is going to be our beta squared. Right? I was going to write just that. So beta squared is K1 over script D times that length squared. And beta is a very, very important modulus in mass transfer. Remember, it was called Biot modulus for heat transfer, but for mass transfer it's called beta, which is equal to the square root of K1 over script D times B, is known as the Thiele modulus. And it is a very important modulus because it shows you the relative importance of reaction speed as measured by the reaction rate constant, K1, and the speed of diffusion of the reactant inside the catalyst particle. Of course, you're responsible for remembering the Thiele modulus. You can pronounce it Thiele, that's fine. You speak German, right?
My mom does, but I don't.
Your mom does,
Yes.
but not you.
Yes.
I think the Germans have like TH, they go like Thiele, Thiele. So they almost aspire to the H instead of, okay, go to Germany. Okay? Of course, we're not going to solve this equation, right? Yes.
So to de-dimensionalize C, since it's in the second
You
derivative,
just
would you have to divide by
okay,
C
let's
naught
do it-
once or
let's do it on the
twice?
spot. Yeah. Divide by C0. Divide by C0. That becomes phi.
But you only need to divide by once?
Yeah, because we only have, in the previous problem, we had two constant temperatures. We had T0 or TF, T fluid, and T base, right? We had two different temperatures that were constant.
Okay.
Here we have just one, so this is easier in that regard. When you non-dimensionalize, it's easier for this problem. I have left pretty much everything on the board so that you can ask questions before we go to the next problem.
For the boundary condition there, should C equal sub-zero?
Oh, very good. It was a mistake, right? I said C0, I remember, but I wrote 0. If you do that in the exam, thinking C0 but you write 0, you get what you wrote, right? Things that I can do with impunity, but you will, not you, them with penalty.
So if we write 100.
Questions? Yes.
Why does the non-dimensionalized version for the boundary conditions, there's the phi with the xi subscript? Why is that?
This is the first.
Yeah. Okay. Oh, okay. Right.
Remember
Yeah.
the notation that we used last time?
Yeah.
In mathematics, in several mathematical textbooks, actually, they use this notation. Instead of writing d phi d psi, they write phi sub psi. In a differential equation, for example, d squared y dx squared minus a y equals 0, they wrote this as y xx minus ax equals 0, meaning the second derivative, double subscript, sum. So I'm preparing you for books that may be using this notation. Any other questions? In other words, the problem of, let me finish this statement and then you ask the questions. The problem of heat removal from a straight fin, because that's what we considered last time, a straight fin, is mathematically identical to the problem of removing reactants by means of having a reactor. Yes, now who had the question first?
So still explaining why the image
Here, to explain what?
is why the graph
Why the what?
the profile
Oh, why it looks like this? Okay, so imagine that we are consuming something here, right? We're the catalysts. And we're consuming a reactant. That reactant is coming from there. And when we consume it, like, let's say eat it. Something comes in, we eat it. Well, that's not it. Because we produce something. So we get, okay, we breathe it, right? Now, don't you agree that as it comes in, it reduces itself in concentration because we eat it or drink it? But that's why the concentration becomes smaller. In other words, this is the surface. You have the highest concentration of reactant on the surface. But as it is moving inward, it becomes smaller and smaller and smaller and smaller and smaller. And this picture is the same as this. Okay? Well,
So, in terms of the model of the thing itself, the concentration is seen on both sides, at both faces. So, is there product leaving and being filtered out?
yeah, but the balance is only written on. So this is a very interesting question, because I always had that question as a student. Why don't we deal with the product? Because we are just balancing the reactants. This is a rate and mass or mole conservation rate only for the reactants. So those are moles of products. They are different. So it's like oxygen going in and CO2 coming out when we breathe it, right? Any other questions? Okay, because we're going to move now away from this. And we're going to move to the more, actually, catalysts are not made so much as wafers, even though there are important practical problems with wafers being catalysts. But most of the time when you pack reactors, you pack them with spherical catalysts and with cylindrical catalysts, like pills. And the reason is you can pack them better. And if you get too many stacks and they go one on top of the other, they don't allow the gas to flow through them and get a good efficiency of establishing a high concentration of reactant on their surface. Okay? Therefore, it is preferable to have spheres or cylinders. Are you coming back soon? Very quickly. Because I have to wait now for him. Because the things I'm going to say are too. Do you have questions? Okay, I'll tell you what we're going to do once he comes. Once he comes back, I'm going to draw this picture for a spherical catalyst particle. And I will also draw a cylindrical catalyst particle that will look like a piece of chalk. For the cylindrical catalyst, okay, with a high. So for a cylindrical catalyst particle, we're going to assume that from this side and from that side there's no flow. It's like if they're insulated, so that we can ignore end effects. And then we're going to draw balances for the two. One will be drawn on the left-hand side, one balance will be drawn on the right-hand side. So I start by erasing what I told them now is that we're going to do spherical on the left and cylindrical on the right. It is a spherical capital. Not capital. I don't know why this keeps coming. I must have had a discussion with somebody. Okay, these are the pores inside the catalyst. There is a capital R for radius, and of course there is an R, an R for radius and a script D for diffusivity. On that side of the blackboard, we're going to draw a cylindrical catalyst particle like this, with length L and radius R. Again, there are pores on the surface of this that move into the body of the particle. We have done this several times for the cylindrical geometry. By drawing, we used to draw in fluid mechanics a rate of momentum balance. Then when we did the heating of the electrical wire, we wrote a heat balance. Now we are going to write a mole balance on a thin shell. Cylindrical shell, also known a very thin annular space, very thin annulus. At R and R plus delta R. Just like before, we're going to have J times some area, which you will tell me, at R minus J at R plus delta R minus K1C times something else is equal to 0. And you're going now to fill in the blanks. This is the flux, the molar flux multiplying in area. Gabrielle, what is that area?
2 pi r l.
Perfect. 2 pi r l. Thank you. And the same one will be here. 2 pi r l. Just like in fluid mechanics. This has to be, of course, not an area, but a volume. Okay?
Mm-hmm.
So, what is that going to be called?
2 pi r l delta r.
That's it. 2 pi r is the volume of that thin shell. As we have done before, we're going to cross out the constants. 2 pi L, and rewrite the differential equation as J R at R plus delta R. Of course, this is, we have done it so many times that it should come like automatic. In other words, we put the R plus delta R first, multiply the whole equation by -1, minus J times R at R plus K1C times R times delta R, but we also divide by delta R. It's going to be equal to 0. And then, when we take the limit of this, as delta R goes to 0, we're going to get d R times J dr plus K1C times R is equal to 0. What is the next step, Will?
We substitute E and J.
Right. By Fick's first law of diffusion. And when we so do, we get the following. We get V dr R dc dr minus K1C is equal to 0. And I had an R here. I'm going to choose to put it there for things that we're going to learn in a bit. Have you followed this? The conditions, so we do have now differential equations. The conditions are that at small r equal to 0, we have the derivative of c being equal to 0, but we also have a smarter way to say that. Yes?
Why is it minus K1?
Because when you substituted J had a minus. Okay. Okay, so at r is equal to 0, C is going to be what? Steph? That's with an F.
Fick's law.
Remember the flow through tube. Same thing. What you learn in one applies to the other. Cylindrical, right? We said that it's the same d. At the time with velocity dv dr equals 0 was equivalent to saying that the velocity is phi e.
Infinity. Finite.
Finite means not infinity.
No, I know.
Right? Finite. Finite means not infinity. It doesn't go to infinity. And of course, at small r equal to capital R, C is equal to C0 because on the surface again we have constant surface concentration. Okay? Let us non-dimensionalize this. We have done this type of non-dimensionalization dimensionalization in fluid mechanics. Again, we're going to have the same psi equal to small r over capital R. Phi is equal to C over C0. Please follow now the accounting of capital R's. We divide this by capital R. We divide this by capital R. We haven't changed anything, correct? But when we divide this by capital R and this by capital R, it's like, in order to keep the accounting correct, we have to multiply this by R squared. Okay? And of course, we can divide C by C0 and get our phi. And the differential equation would be 1 over psi d psi d phi d psi minus beta squared phi is equal to 0, with conditions at psi 0 phi is finite, and at psi 1 phi is 1. Do you have questions about any of this? So far in fluid mechanics, we have not done any problem experience. Yes.
So when you substitute the J, where is the molar?
Oh, I forgot it. Thank you. Wow, that guy is on it. Very good, Alexis. You see what he said? I forgot to multiply here by delta, or script D, which means that comes under there. Thank you. Since you said that, our beta square in this case is going to be K1 over script D times R squared. In other words, before we had B for the characteristic length, the fixed length was half of the slab thickness, and this is R. Okay, now, we haven't done something, a balance, previously for spheres. We've never done it. And we're going to do it now for the first time. How do you think it's going to look, the element that we're going to choose to write a balance on? What does it remind you? Something that you probably used or ate part of it today. Loud? Egg? Egg. But round, like totally serpent's eggs are usually completely spherical. Well, almost spherical, right? Or small birds have rounded. Well, some birds, but they make more spherical eggs. It has to do with gravity, how the eggs look like. So, imagine, please pay attention. Imagine having an egg that is completely spherical and somehow stripping everything from the inside, like we make a hole, everything comes out, and we have the eggshell. Can you picture that? That's the element that we're going to use to write a balance.
So ping pong.
It's going to have it's going to have a thickness, of course, delta R. And now, for this element, for this spherical shell element, so we're going to call it spherical shell element, we're going to write our mole balance. The mole balance is going to be as follows. Imagine that this, of course, is coming also this way, right? It's going to be half of the spherical shell protruding outside the blackboard, and the other half going inside the blackboard, because I cannot draw spheres. I can only draw circles, thinking of spheres, hoping that all of you are thinking of sphere, not of a circle. If that is the case, this is going to be the flow of reactant in the growing R direction. We know that reactant actually is coming from the outside, right? But always when we write a balance, even when, if it is a dollar balance, even if our checkbook or our balance in the bank decreases, we still write how much money we have today versus minus how much money we had yesterday. We always start writing later minus what comes earlier, and the flow comes from earlier. In other words, the flow of money goes from April 24th to April 25th, and that flow can be negative. If our bank account decreases, we're still considering the flow of money going in the increasing time direction. Same thing with this. Minus this that comes out of the shell, and those are going to be J times some area at R minus J times that same area at R plus delta R, minus the amount that is consumed and that amount that is being consumed is going to be K1C times something. And again, I'm going to ask you, Alex Simon, what is this area? The flux is multiplying the area perpendicular to the flux. Can you tell me in terms of the eggshell, what is that, the area of the eggshell? It's the area of the shell on the inside, right? So imagine we're very microscopic and we're inside the eggshell and we look all around, that's the area. So what is that area?
It'd be 4 pi r squared.
Very good. It's the area of a sphere. So if you are inside a spherical shell and you look around, the area that you see is 4 pi r squared. Small r, right? Because the area of the shell is small r squared. And this will be the same, 4 pi r squared. And Jasmine, what do I put here?
The volume.
Very good. The volume of that eggshell. And what is it? Oh, but you don't have to remember these things. That's the wrongest thing to do, to try to remember. So let me help you. Now imagine that topologically, because that's a very thin thing, right? You break the shell and you flatten it all over here, and you put all the pieces together. So that shell, you flatten it and it becomes like this, one plane, has a volume. What is it? Dominant. No. Long. Look.
You're talking just of the element.
Yeah, only of the eggshell. The eggshell being very, very thin. Remember, the eggshell is very, very thin. No. What is your name?
Natalie.
Natalie. You have the answer? Come on, make them put them to shame. This Alex.
4 pi r squared.
No.
Squared delta r.
Say that again.
Delta r.
Loud.
4 pi r squared delta r.
Do you hear? Did you say that? Okay. Okay. So, the area of the shell, please pay attention. The area of the shell, when you flatten it out, is how much? If you take all the pieces of shell and you make this, how much is that? 4 pi r squared times this thickness, delta r. Right? So it's going to be 4 pi r squared times delta r. Any questions up to this point? Yes.
Why is it not big R?
Why isn't it big R? Because the eggshell, this, does not have radius big R. Remember, the eggshell is within the big sphere. It's like a fictitious, something you think about. It's not the real. You know. Anybody still has not understood this? I don't mind trying to explain it differently if you cannot get it. Get it now? Caitlin? Over there? Down? Are you okay with that? Gabrielle? No problem. Dylan? Okay. Well, if that's the case, then we do like what we always do. Divide by the constant, which in this case is just 4 pi. Then write this equation as j r squared at r plus delta r minus j r squared at r divided by delta r plus k1 c r squared is equal to 0. And take the limit of this as delta r goes to 0. And if we do so, the differential equation that we obtain is going to be d dr r squared dc dr. No, let's not get to that point. So we have r squared j plus k1c r squared is equal to 0. In other words, the derivative is the derivative of j times r squared. The next thing will be to substitute for j by means of negative script d dc dr, which shall give us d dr r squared dc dr minus, because the sign changed, k1 over script d times c is equal to 0. And again, I choose to put the 1 over r squared multiplying that. If we do exactly the same non-dimensionalization, namely, if I divide this by r squared and this by r squared, I haven't changed anything. But if I account for the two other r's, over r, again here I pick up a capital R squared in order to keep the same the equation intact, which of course will give us the differential equation that says 1 over psi squared d psi squared d psi minus beta squared, phi instead of c. Phi is going to be equal to 0, and it's going to share the same boundary conditions exactly as the cylindrical one. Now, this is some stuff that you probably have not seen before. At least the way that I'm showing them to you. You should have seen them. But a lot of the times the most important stuff is left out of the curriculum, right? In many subjects, so why not in mathematics? We know that this is a second derivative, okay? And this differential equation looks just like this one, except that instead of a second derivative, we have this one. So if you were doing mathematics 200 years ago, you might have been tempted to call that like a cylindrical second derivative, right? And when you look at this equation, again you have this operator operating on phi, and again, if you were long time ago student of mathematics, you might have said, well, this is like a spherical second derivative. They did not call it that way. They called it differently because of a big name in mathematics, Laplace. So this is known as a Laplacian. But let me show you something that is shared by these three derivatives. First of all, are you following what I'm saying? Is there anybody who missed it? The first derivative, I can write it also like so. 1 over psi to the 0 power d psi to the 0 power d phi d psi. Do you agree that this is exactly the second derivative as you know it? Because psi to the 0 power is what? 1. And this is also 1. So what happens is, as you go from a plane geometry, where how many ways of curvature do you have on a plane?
0.
0. And when you take a plane and you want to make a cylinder, how many times do you curve it?
1.
So this is psi to the first, psi to the first. Now, if you want to make I cannot make a sphere, but as I curve this way, I also have to curve. Can you curve it? Yes, that's right. And from this way. So we both curve, and we get a sphere. So a sphere has like double curvature, right? Because you take a plane. So those are things like in topology, but actually they're shown also in this most basic differential equation, where you have no curvature at all, 0 curvature for a plane. You have 1 curvature for cylinder. You have double curvature too when you make a sphere out of a plane. But these differential equations look surprisingly similar to one another. Now, last time we showed how you are now experts, right, at solving this differential equation. You were already when you took applied or first week, second week of applied math. But after last class, you have to be real experts, otherwise, right? You can do it. But you cannot do this. And you cannot do this. But you are going to learn how to do this in the next, not in the next 10 minutes, in the next 10 minutes plus most of the class next time. Okay, so I want again to tell you that what I have put in this is the so-called Laplacian operator. Laplacian operator that operates on phi, and for a plane, the Laplacian operator is simply the what? The second derivative. Okay? It looks different for cylindrical coordinates, it looks different for spherical coordinates. Now, what I'm going to tell you is that both the cylinder equation and the spherical equation are part of the so-called Bessel differential equation. Have you heard of that name before? Bessel. Right? I don't write the curriculum. If I wrote it, you would definitely be hearing it much more than you have. And the reason is that spherical problems and cylindrical problems in all the sciences, in large part, end up being parts of the so-called Bessel differential equation. You are going to appreciate the Bessel differential equation by starting a totally cookbook method. And then things are going to be making more sense. First, you're going to be looking at what I'm going to give out. This big over there. There is plenty, so yeah. There. Get a bunch back there. Yeah. Yeah, because at the center it's finite, from the surface it's 1, it's a 0. Yeah. I want you to be looking at equation 174. I'm warning you that today, because we're going to stay here 5 more minutes than last time, it will not make any sense what we're going to be doing today. After 10 or 15 minutes of next class, it's going to start making a tremendous amount of sense. Okay? But you have to just tell me whether you understand what I'm telling you, not whether it makes sense. In other words, if I tell you that this is a car, do you understand what I told you?
Yeah.
It doesn't make sense, it's not a car. Yeah, I get that. But did you understand what I told you? If you spit out to me, yes, you told me that this is a car, then we're fine. For today. Do you understand that? Okay, so the generalized Bessel differential equation says that it's written like equation 565. Because of time, I will not write 565. Look at it. Are you looking at it? We want to take our let's say cylindrical differential equation and write it and match it to that. How can we do that? So I will go to the cylindrical differential equation and write as follows: d psi d phi d psi minus beta square psi phi equals 0. All I did is multiply by psi. Right? I mentioned that we're looking at the cylindrical equation. Like this one. Just in case, let me circle it. We're looking at this equation here. This is the cylinder. Okay? Then I want the first term of the generalized Bessel differential equation to look exactly like the first term of the equation that I have here. So what do? I expand this derivative because this is the first derivative of a product. This times that. So first I'm going to keep psi constant. Take the derivative of this, and then I'm going to keep this constant, take the derivative of this, which will just give me d phi d psi. You see that or not? And then minus beta squared psi phi. Now, the first term that I have on the generalized Bessel differential equation is what? X squared times d squared y dx squared, right? In order to make this exactly like that term, what do I have to do, Lan?
Multiple times.
That's it, multiply by psi. So I will multiply this by psi to get psi squared, psi, and psi. And of course, this whole thing is equal to 0. So now I have the first term matching, being identical to the first term in the Bessel, generalized Bessel differential equation in the handout that I have given you. The next thing I'm going to do is figure out what those other constants are. I have constants A, B, C, D, S, and so on. By playing a matching of the terms game. So I want now the second term to be exactly like the second term in the generalized Bessel differential equation. Well, what do you think A should be? Or B should be? What is the easiest way to make that happen? Making B equal to 0, right? If I make B equal to 0, I get rid of that extra term there. And what should A be? 1. So already I have found A and B. Alex, Bird, see that?
I don't see where that is. Oh.
If A is equal to 1, 1 multiplies X. If B is 0, you don't get it. You don't get that term at all. Then I go to the last term, and I notice that because B is equal to 0, 2 of the terms go automatically to 0. See that? The terms that are multiplied by B. And then what is C going to be? Also, C is going to be equal to 0. Let me write that whole term. We have C plus dx to the 2s minus b times something plus b squared times something else. That's the term that multiplies y. Do you see that? Now, if the b is 0, that means the last 2 terms are going to be, of course, 0. Right? Because b is 0. We have to get c and d. Well, d cannot be 0 because we have psi there, the second power. So what does c have to be, Ninha? Very good. C has to be equal to 0. And then what does D have to be? Has to be, because we have a negative sign, negative beta square. And what does, so D is going to be negative beta square. And what does S have to be?
1.
1. Very good. So now, what we have done is we have taken our differential equation, and we have, after, of course, I told you that it is a special case of the Bessel differential equation, and we have found these constants that match it exactly to the generalized form of Bessel's differential equation. And then equation 66 is the answer. It says, once you get that, you are going, this is like a cookbook recipe. They tell you do this, do that, and you don't know what will come in the end. You know, take so many spoonfuls of sugar, so much water, so much milk, put it together. You don't know what, maybe you don't, right now you don't know what you're making, but you're just following this recipe. Okay? And we have to stop. Do you have questions? Now, please, by Thursday, in order to appreciate Thursday's class, review this extremely well, know it by heart. All this that we did.